Right, welcome everyone to another series of HES colloquium talks. Just a reminder before starting that make sure that your microphones are muted during the presentation. So today's speaker is Dr. George Gao, and Dr. Gao is a quaternary geoscientist with the Ontario Geological Survey. His research project is far north terrain mapping in Northern Ontario. His research interests are sedimentology and stratigraphy with a focus on Neogene and Quaternary period, paleoclimate reconstruction, and surfacial geochemistry for indicator minerals. He was one of the outstanding reviewers of 2015 for Canadian Journal of Earth Sciences and received nomination for Best Paper Award of 2011 by the same magazine. George obtained his PhD from the University of Cambridge, UK, and his MSc and BSc degrees from the Chinese Academy of Sciences and Xinjiang University, respectively, in China. Without further ado, Dr. Gao, you can go ahead and make your full presentation and start the talk.
Oh, thank you. Thank you, Mustafa. Thanks for everybody's attending for my talk today. Give me a second. Okay, my talk gonna be focused on some sulfur-rich ferromagnetic nodules found in an old lake deposit formed during the last interglacial stage around 120,000 years ago. So this is the study site. Okay, now this work is a team effort, right? So I like to take this opportunity to thank my the other team members here, like Dr. Hewitt, Dr. McDonald, and Dave Crabtree, and Charles Turton. Thanks for their efforts and contributions, as well as their patience. Now, introduction, right? Why this area, this deposit, this area is important, right? Because the stratigraphic records in the Hudson Bay Lowlands of Canada can provide key information for the past glacial and interglacial conditions, right? Because this region is located near the geographic center of the Pleistocene Laurentide Ice Sheet, right? Now, in this region, basically you can see nonglacial fossiliferous deposit quite commonly occur below the Wisconsinan tills, right? The pollen data, people did a lot of pollen analysis of these nonglacial deposits, right? Basically, the pollen indicate the vegetation, which is very similar today, and so the climate was interpreted was very similar to today, right? So this is the one. However, one thing we need to know that the last interglacial was warmer than today. So now you don't see any warming from this pollen data. Then some people just come over and ask why this deposit was last interglacial stage, right, or interglacial stage. Why it cannot be like interstitial stage, right? So there is a lot of debates going on, right? So recently we studied the calcium deposit of last interglacial. We refer to that as a Weberquid bed, which is located on the Wisconsinan River in the Hudson Bay Lowlands, right? So we use the radiometric dating, a lot of environmental studies, sedimentary studies, and trying to constrain the age and to trying to reconstruct the past climatic conditions, right? During the laboratory sample preparation, we just find by accident some sulfur-rich ferromagnetic nodules, right? So this has led to a detailed study on those nodules. We're trying to understand why they are there, what is the associated sedimentary, geochemical, and the climatic conditions associated with them during their deposition. Now, this is a slide to show the study area. You can see here, this is the Wisconsin River is located here. This is a main section, right, located here. Basically, the physiography or the landscape is really boggy here. This is just large piece of wetland, right? It's a lot of open bogs here, right? You can see basically this is all bogs, right? And good vegetation like boreal forest or woodlands grew on along the riverbanks and on raised area where you have a little bit of drier substrate or soil, right? And here a little bit about the climate here. The climate here is very cold, right? The mean annual air temperature here is -3°C. So it's pretty cold, right? So and this very cool condition. So there is a discontinuous permafrost in here. So look at this, yellow arrows that indicate the raised peat plateaus. We call peat plateaus. Those peat plateaus actually are cored by ground ice. So this is within the discontinuous permafrost area, right? Okay, there are a lot, have some small pulsars, right? But on this scale, it's too small to see them, right? Now this is a sketched stratigraphic column. You can see this is the Last Interglacial deposit. We call that the web quake beds, right? This is about 9 meters thick. So most part of this deposit actually is below the river level. So this is Winooska River level over here, right? Okay, then above this interglacial deposit, we have a till deposit, right? There are 3 tills: lower till, middle till, and upper till, right? Then above the till, we have post-glacial deposit of glacial lacustrine, glacial marine, and recent peat deposits, right? So this is basically stratigraphy we see in these riverbank exposures. Now the nodules actually are found in the uppermost part of the Last Interglacial lake deposit, right? It's in the uppermost 1 meter part. Okay. Now these are photographs to show what they actually look like in the field, right? So this is the Winooska River. We're looking downstream, right? So this is the river section, river exposures, right? So you can see you can use the trees as scale. So the tree is about 10 to 15 meters tall, right? So basically this section is about 13 meters deep, right? So the M is a triangle, means here that is the main section we based on was study, right? So this is the view of the interglacial lake deposit. You can see it is very, very organic, well laminated and bedded organic silt, right? This is a enlarged view of this interglacial deposit. You can see the well lamination and bedding, right? You can see here. And also you can see there are a lot of wood fragments, right? Pieces of wood. You can see here is wood, right? As indicated by these arrows, right? Now this photograph shows the upper contact between the till and this interglacial deposit, right? You can see the contact basically is very sharp. We think that's obviously it's erosion contact. Now this is the overlying till deposit, but this is not a focus of this study, just a quick look. So the lower till, look at the color, enlarge it here. This is the middle till, look here, enlarge here, and this is the upper till, you can see here. And this is glacial lacustrine silt clay, which is related to the glacial lake, Lake Agassiz. I'm not sure you ever heard that, but I think this is very, very popular, very famous old lake, which occurred around 10,000 to 8,000 years ago. Okay, then this is again, this is a column section, but here I show some physical and geochemical measurements of features about this interglacial deposit or web quake beds, right? You can see the grain size analysis. You can see this deposit is dominated by silt, right? Over about 75% of the deposit is silt, right? And you have this total organic carbon content, right? You can see here at the base of this deposit is a little bit poor, but since from about 6 meters upwards to the top, you can see the deposit is very, very organic, right? There's a lot of organic deposit, organic material in this deposit, right? This shows the total carbonate content, right? You can see which is the deposit is very, very calcareous, which contains the 20 to 30% of total carbonate. Now this is the said nodules, right? This is massive, right? This I picked up from this sample, the CG50. You know, this is a lot, right? And but the neat thing to look at, this is the samples from that sequence. So this lower sample is almost 9 meters near the base, right? This is the very upper contact of these lacustrine deposit, right? You can, in the lower part, basically it is barren. We don't have such nodules, right? And this only, well, most of it, I would say most of it happened in the uppermost part, uppermost 1 meter also part of the sequence. So this is the depth, right? 84 centimeters. We don't analyze small samples between these two, right? 36 and 22 more. But basically, this is they occur in the almost upper part of the sequence, right? Okay, this is a enlarged view of these nodules. You can see this is they have very interesting shapes, right? Some a very irregular shape. The other one had a little bit platy shape, and a lot of them had this kind of rod-shaped appearance, right? Okay, and because these ferromagnetic nodules have strong magnetism, basically I picked up them use handheld magnet to pick it up them. So it's very easy to pick them up. So you do that, you also pick up a lot of fresh magnetite and rock fragments containing magnetite, right? You can see here, this is the ones, right? Those very interesting to see that those magnetite materials actually most located in the basal part of this sequence, right? Further up, you can see it become rare and most time they're absent, right? They're not there, right? So you can see there is a very clear reverse correlation between the ferromagnetic nodules and the magnetite minerals, right? And the inverse correlation. Why is that? We're gonna discuss later on. This has something to do with things, something to do with the redox condition, right? That means in the upper part of the sequence during the evolution of the lake, right? The lake tend to have more reduced condition. That means the lake tend to have less oxygen or poor oxygen in the lake water or no oxygen. So that can create this kind of reduced condition. And this kind of setting condition, magnetite tend to be dissolved. So the iron oxide of magnetite can dissolve, right, in this reduced condition. That's, we think this is the reason for that. Excuse me. We also use the XRD to analyze the compositions of these nodules. These are results. You can see these nodules contain native or elemental sulfur. That's the S here, right? And also greigite. This is the red peaks here, right? This is a GR. This is a greigite. And iron oxyhydroxide, right? Like goethite and lipidocroside, right? This is here lipidocroside L, right? So these have a kind of, these are melange, right? Melange, mixed minerals, all just lumped into these nodules, right? Now, a little bit about the greigite, right? The greigite is a mineral discovered in 1960s, right? By geophysicists basically defined greigite. This has very strong magnetism, right? This is this mineral just is the iron sulfide equivalent of magnetite. So this has very, very strong ferromagnetism, right? So that's why the nodules are very, very magnetic, right? How these greigite minerals are formed, basically is well-established observation. This mineral forms from a solid transformation from white and anoxic hydrous condition. Anoxic means oxygen-free, right, conditions, right, or limited oxygen condition. condition, right? So this is no question for that. This is well observed phenomenon of the process. So this is no question about this, right? Now a little bit question about this item, right? A lot of people believe or suggest that this mineral greigite is metastable, right? It radially transforms to pyrite, okay, pyrite, right? Because basically a lot of people believe that. However, we find no trace of pyrite in these nodules, right? Only greigite, right? So this means the lack of pyrite means that this transformation has not occurred. Why that? What is the reason? We don't know. But however, this is consistent with some recent laboratory work by Dr. Picard, right, and her team. They just have recent paper published in late 2 years ago. So that's the laboratory. Because that means the greigite, you can create these kind of minerals in laboratory, right? So they have very well observed study in there. So they also didn't see this transformation. But anyway, so this is one thing we noticed, right? Now this is total sulfur, and we use the ICP-OES method to detect the total level of sulfur. This is the ICP-OES stand for this, right? If you're not familiar with this methodology here, right? You can see this is for the whole section, the overbank section, right? This is till, this is the web bed, this is the post-glacial lake and marine deposit, this, right? You can see the total sulfur level actually between all these deposits are very similar. And you can see here, right? This is in the web base, the Last Interglacial deposit, and in tills here, and you have a lot of analysis here in the post-glacial deposit. You can see this is all even those within the marine deposit, right? All those marine deposit. The total sulfur there are very similar to what we see here within the Last Interglacial web base, right? So this is also very interesting, right? Now we enlarge this part web base to here in this panel. You can see here this is the total sulfur, right? It goes up here, and then you have increased the sulfur in the upper 1 meter of this sequence, which is corresponds to the formation where we find the nodules here. So that really this total sulfur also confirms that this is true, right? This is also to give you another layer of information about the increased total sulfur in the sediments, right? Of course, in the nodules, we know that they have native sulfur. You have greigite, which is also sulfur iron sulfide minerals, right? The sulfur bearing minerals, right? Now, this is the SEM some images to show internal structures of those some of these nodules, right? You can see some of them that have very amorphous interior structure. Interior, you can like this one. You have a lot of lithic class, like we have a feldspar class, and you may have some piece of organic material just embedded in this nodule, right? And this one looks interesting. This has a well-formed layering structure, right? You can see here, right? And this also has layering structure, but the structure the layering is irregular, right? So it looks a lot of this kind of like brain, human brain shaped structure, right? But it's layering structure, irregular, right? But one thing I need to draw your attention, this is a large piece of feldspar you can see here, right? Because we use the SEM, the EDS EDS analysis to analyze these things, right? But one thing I need to draw your attention is this the bright outer rim, which exists for every single nodules we studied, right? You can see here and see here. You can this all white bright outer rims here and in here, right? You can see here. But if you look further, you can find this outer rim, bright outer rim, actually cross-cut the internal layering structure. You look at it here, right? It's very, very obvious, right? So this really indicates to us that this bright outer ring feature is a post-depositional feature, right? This caused by weathering process, right? The other thing we need to think, right? If you have this kind of well-developed weathering ring of outer rim, that means that these nodules being there for a while, they're not formed recently, today or yesterday. They have been there. They must have been there for a long time to get this kind of weather feature, right? To kick in, right? To form these bright outer rims. Okay. Now this is another one to show this layering structure here, and this is part of enlarge this part to here. You can see this layering structure. Actually, along this the bedding structure, we have this kind of blade-shaped carbon-rich mineral in here, right? We don't know what type of the mineral is, right? But it's orthogenic mineral, right? But it's carbon-rich. We think it's probably calcite, but we're not so sure, right? Okay, and then we have this kind of further enlarge this matrix. We see these goosebumps like spheroidal particles, right? This kind of bumps right here, right? We think they are the gray guy, but we cannot confirm that. We just think they are, right? Because we don't have the means to analyze each of these bumps, right? Because and EDS, you use ADS to analyze. EDS has a zapping point about 2 micrometers, right? But these are nanoscale. It's about 20 to 30 nanometers size, right? So this is too small to use the traditional the EDS method to analyze, to pinpoint them, right? Okay, we can look at a little bit about this area, because we use the X-ray to map this area, trying to figure out what is this mineral is, right? Now this is the base grain. You can see here. This is a scanning line. You can see here. So this shows the result. This is carbon. It really has a high carbon, right? You have high carbon here. A little bit, higher calcium. It's not much, right? But there is show some carbon, right? But this has low iron here, right? So look also in the matrix, iron looks very, very evenly distributed, right? Here, right? This is iron, and then this oxygen. Now this also has low oxygen, in particular along the edges, right? All the side between the matrix, right? You can see the low oxygen things, and this is one is sulfur. Sulfur is low sulfur, and also look the sulfur in the matrix, right? Sulfur tends to be very heterogeneous distributed, right? So this is things we know that. But again, we don't know what this mineral is. We think it might be calcite, but the calcite has a lot of oxygen, right? So there's carbonate mineral, right? But the carbonate has oxygen in there, right? But then this looks at the low oxygen. So right now, so we don't know that for this mineral. Okay, we're gonna look at different topic about sedimentary conditions, right? To understand the geochemical and sedimentary conditions associated with these nodules, it's very important to understand the sedimentary conditions at the time these nodules form in the lake, right? Now, one thing we know that those very nice argillaceous texture and the lamination of the Weber bed indicate a lake, right? Indicate a deposit which was formed below the wave base in the lake, right? So this means that if you have shallow lake, you have a strong wave, right? The wave base gonna erode the lake floor, right? This way, they're gonna homogenize all the sediments, right? You're not gonna have this kind of nice lamination or bedding to be preserved. They're all gonna be destroyed, right? So that's why it's important we know that it has to be below the wave base in a deep lake, right? How deep it is, we don't know. We will never know, but these are lakes, right? However, we have good observations for ocean settings, right? Like in open ocean shelves, right? So dominated by waves and storms. So we know that this depth is about 7 meters deep, right? Under fair weather conditions, right? So this one. So we use that to apply these depths to the lake. This thing lake probably has these depths, right? Now this could be a little bit shallower, say 5 meters, or could be more deeper than that, say 10 or 12 meters, right? But this is okay. But at least one point we know that the lake cannot be too shallow. Say that the lake just 2 meters deep, then that did not work. They're not gonna have this well-developed lamination in such a shallow settings, right? So we know that. And also, you know, the web base itself is 9 meters thick, right? That means that you have a lake basin at this time at least 9 meters deep, right? So, but then we have to consider the erosion by glacier. So the original thickness could be much deeper than that. So the basin lake could be much deeper than that, right? Now, this is a very also good observations, right, in Northern Ontario, because we have a kind of lake studies, field station west of Thunder Bay, that funded by federal government, right? Study the northern lakes in Northern Ontario. So lakes with these comparable days in Northern Ontario are stratified in summer as well as in winter, with water overturns in autumn, right? So the stratified in summer during the fall time, like time now. So the surface layer water become cool and gonna sink. That's overturns, right? And this kind of occur every year annually. This is gonna create very, very dynamic thermal and redox conditions. Now look at the geochemical conditions associated with these nodules, right? Now, one thing we know that both natives or elemental sulfur and gray guide, right, need hydrogen sulfide for their precipitation in lakes, right? So this is the things we know that, okay? And also know that in lakes and oceans in nature, right, this gas, hydrogen sulfide, is produced mostly by sulfate reducing bacteria. We call the SARB, right? This bacteria reduce and utilize sulfate in lakes and rivers, right, to decompose organic matter and anoxic condition. That means and oxygen-free conditions, right? They cannot have oxygen. Oxygen is a poisonous to this RB, this kind of bacteria, right? Now this process is called microbial sulfate reduction, called the MSR, right? Okay, why we have the nodules? Now we know that we have the reason we have this kind of this lot of nodules that because of the enhanced MSR and increased release of hydrogen sulfide in the lake during this particular level, right? So this is a very, very reasonable, we can come to conclusion of that, right? So then because these nodules only happen in the upper part of the 9-meter sequence, and then we think something must have happened on the controlling factors which controls this MSR process, which include organic carbon, pH level, redox conditions, sulfate supply, and the temperature. We're going to look at that briefly for each of the factor. Now, organic carbon, right? Organic carbon also very essential. You need the food, organic carbon, for this bacteria to live on, right? And now we know that in from this analysis, we know that the deposit has a lot of organic material, right? You see that from the photo, the sediment, and from the analysis, right? This is due to organic carbon, right? The basal part is organic poor, right? But anywhere above 6 meters above, right, you can see this is very, very organic, right? So this is not, so we think at the time the lake, during the evolution of the lake and during the deposition of these nodules, the organic should be readily available. This should be more than enough for those little bugs to live on, right? So organic is not a factor which caused the deposition of these nodules, right? They are everywhere, right? Okay, now look at the pH, right? pH also very important, right? We know that those bacteria lives well, right? And grows well, right? At the neutral condition, at pH 7, okay? And their growth is inhibited. They almost cannot grow when pH drops below 6, right? Okay, you can grow. This, bacteria is made of protein, right? This is even you have an pH higher than 8 or 9. This is also gonna kill them, right? So they're not gonna grow well, right? So we don't know. We cannot measure the pH value for this geological deposit, right? Lake deposit, right? However, we can look at the carbonate content in these lake deposits, see how they looks like, right? Now we know that this lake deposit has high total carbonate concentration, right? Between 20 to 30%. It's very calcareous, right? So that means during the time the lake floor is the sediment on the lake floor is very calcareous, right? Lakes, that means the lakes has a very, very high buffering capacity to buffering the acid input into the lake, right? Okay, this is something we just interpret that, right? Now we look at the modern lakes and rivers in this area. All the modern lakes and rivers in this area with such a calcareous substrate, right, a lake floor, have a pH of 7 to 8 in that region. So this is almost very, very common. So we have a lot of study in this, and we know that. So this is one, right? So based on that, we think, right, the lake, so the pH value at the time was sustained at a neutral level, actually very likely within the optimum pH range for these bacteria to live on, right? So we think the pH is not the factor that created this the deposition of the nodules, right? Now redox conditions, right? There's redox that's related to the lake. We already discussed a little bit about the stratification and the collapse of the stratification, right? So we know that during summer lake becomes stratified in summer and winter, right? As the modern lakes do in this with these kind of depths, right? In this region, right? During the summer stratification or winter stratification, the oxygen in the bottom water of the lake is depleted very fast because the decomposition of the organic matter gonna consume a lot of oxygen, right? This way the bottom water become oxygen free, so we call anoxic condition, right? So so this is a good. So that's condition we need for this bacteria to live on, for this process, microbial sulfate reduction process to go on, right? So we need this prerequisite condition we need for this MSR process, right? And during the fall and spring, lake overturns because in the fall the surface lake gonna cool and water gonna sink, and then eventually the water gonna re-oxygenate the bottom water, right? So the stratification collapse, right? Anyway, so this the water is oxygenated. So then, but however, the good thing that those bacteria still gonna live in the upper lake sediment about 10 centimeters depth below the lake floor, right? Then the MSR process continues, right? Okay, so that's something we need to bear in mind, right? So these redox conditions, thermal redox condition happens annually. So every year do the same thing, right? The establishment of stratification and then the collapse of this stratification in the fall and spring, right? So we think that generally this process alone cannot account for why the nodules formed in this particular interval in the lake sequence, right? So this is not, we think this is not the answer for that. Now look at the sulfate supply. Sulfate is also important, right? In lakes, right? We have to have a sulfate for these SARB, the sulfate reducing bacteria to live on. This is also their food. They need these things, right? So in lakes and rivers, lakes and rivers, these sulfate actually come from degradation of sulfur-bearing minerals and compounds, right? During the degradation of these minerals, they're gonna release sulfur, including sulfate, into lakes and rivers. Very important, right? In the Hudson Bay Lowland, we know that there are a lot of gypsum and anhydrite in the late Silurian and middle Devonian Kenogami River and the Moose River formations right in there, right? So those located to the north and southeast of the study. So we have a lot of gypsum, this kind of the sulfate minerals in there, right? And also the glaciers, right? When ice sheet or glaciers advanced always out of coming out of Hudson Bay and James Bay, right? Always come from there, these oceans, right? When they come out of there, they're gonna bring a lot of sulfur-rich marine mud into the superficial deposit, right? So this is a lot of sulfur material in that area. So, right, this is the degradation of them is a very slow geological process, right? Okay. Now, so we think that this weather mechanism, right, degradation is a very slow, steady geological process, which itself is very, very unlikely to suddenly cause a sudden increase of this of sulfate in the lakes, right? So we think this is possible, but it is unlikely, right? Okay, so this is, we think this is alone is not the answer for the position of these nodules. Okay, look at temperature, right? Now we know that this bacteria growth and the metabolism is closely related to the temperature, right? Positively, right? A rise of temperature can significantly enhance the rate of the microbial sulfate reduction, right? Kind of really kind of increase that and speed up that, right? The higher temperatures also reduces the dissolved oxygen in a lake, right? This is gonna help create anoxic conditions, right, for the MSR to go on, right? And also the rising temperature can create prolonged or longer short winters, right? A longer summer lake stratification, right? And then the bottom water anoxia, right? So there is the terminology used, anoxia. Bottom water anoxia, which is a prerequisite condition for the SRB to live on and to have this MSR process, that sulfate reduction process to go on, right? So based on that, we think these sulfur-rich nodules are a result of significant warming during this interval. Remember that there's no warming, no much warming. This 9 meter sequence, right? No, not much warming, not warming until the upper 1 meter. Then that during that interval, and we have a strong warming occurred that caused this deposition of these ferromagnetic sulfur-rich nodules. Okay, these the following some of the chart, the cartoon chart to show how this process looks like, right? Now it's all the in particular we look at this microbial sulfate reduction, right? How that happens in a lake, right? This is first one to show that this is just normal condition like today in Northern Ontario, in Hudson Bay Lowland. You have a lake, we'll have a lot of lakes, right? Now during summertime, lake gets stratified, right? So that means this bottom water is anoxic. This is there's no oxygen here, and upper part has oxygen, right? The fish lives can only lives here, right? Okay. In this anoxic part, bottom water, we have this sulfur reduction process going on that produces hydrogen sulfide, right? The gas in the lake, right? Okay. When this lake goes up, they're gonna be this gas gonna be oxidized, right? You're not gonna see that, right? And in the largest part, you can see, let's see the lake sediment below the lake floor, right? You can see here also there is some sulfur reduction process going on in the lake sediment, right? Which is about 10 within the depths of the 10 centimeters below the lake floor, right? So within these steps, so this MSR also goes on. We have a hydrogen sulfide also produced here, right? Again, this is not my invention. This is based on a lot of studies conducted by biologists and biogeochemists, right? Studied on molten lakes. This is the conclusion from them. Basically, this is the 10 centimeter depths below the lake floor. That's where in the lake sediments we can have the bacteria live on here. We can have this sulfate reduction process going on here, right? So this is for fresh lakes, right? In marine setting, in the oceans, these depths is a little bit deeper. These can reach about 1 meter or 2, right? That's because marine water has a higher concentration of sulfate, right? Sulfate actually just diffuse downwards, right? You can diffuse further downward, right? To to the depths, right? So this is, but for the fresh lakes water, this is the depth, about 10 centimeters, right? Further below that, because the sulfate gonna become very limited, of sulfate limited. So this process, the sulfate reduction process, is very limited. Okay. Okay, so say what if we have a warming occurred, right? This same lake, and because this is not ordinary climate at this time, say we have significant warming, right? If you have this significant warming, higher temperature, you can see you can have a higher sulfate reduction rate. You have much more hydrogen sulfide produced in the lake and in lake sediments, right? In this case, and these circumstances, we have these nodules formed, right? In here. Okay, and also the temperature, we know that why is that high temperature warms, that because that increased sulfate reduction rate, and also because this is higher temperature warming, that gonna have longer summer and shorter winter. The longer summer is good, you know, have longer summer lake stratification. So this helps, right, to create this the increase of hydrogen sulfide, right, here. Now this during the, so the summer is just passing, like right now here in the fall time, and the surface water becomes cold, and that the water gonna sink to the bottom. In doing so, that gonna replenish the bottom water with oxygen, right? It's going on here, and you can see the fish can live in the bottom water at this time, right? Again, so this is a chart, in large chart, to see how this is going on, how far this oxygen can diffuse downwards, right? Basically, the oxygen can diffuse downward just a few millimeters depth, right, below the lake floor, right? This is basically about the maximum for fresh lakes is about half centimeter depth. Again, this is not my data; it is from publication, a lot of other studies by biologists and biogeochemists, right? This is their the observations, right? Below this thin layer, with this MSR goes on, these sulfate reducing bacteria still lives here, right? Okay, so now during the so winter time, the lake also gets stratified because during winter time in Northern Ontario, lake gonna be covered with ice, right? So then, so the temperature in the bottom water is around 40 degrees Celsius, right? The surface water and ice about 0 degrees, right? That's the setting, right? Because whatever warming or cooling during the winter time, so the lake water is temperature is very stable, right? It's not gonna, so temperature not gonna affect this lake water, right? So temperature in the lake is cool, right? During this time, we still have, we have bacteria, this SRB bacteria lives here. We have MSR process going on here, but the rate, right, of this MSR process is low, right? So that means that you have limited hydrogen sulfide produced, right? These things are not gonna form nodules, right? Okay. The spring comes, and it's again like what happened in the autumn or fall time, but this time it's like different. The surface, the ice melt, the surface water of the lake become warmed up, is warmed up, right? And the water at the surface warmed up to 4 degrees, and the water become heavier. Then the water gonna sink, right? When it sinks, it's gonna re-oxygenate the bottom water here again, so the fish and move down to the bottom, right? And then this is the same situation that we see during the autumn or fall time, right? Okay, so during this time, this hydrogen sulfide production is limited, but it's still there. Okay, the summer, this is going to go back to summer again. It's end of warming, so we still have a lot, and then we have the lake got stratified. The warming kicks in, right? And you have strong sulfate reduction and strong release of hydrogen sulfide in the lake. You can see here, and also we have more nodules and the form and the origin. Those old nodules probably enlarged, right? So this is a process we think that is why the nodules will form in the lake. So I got the fish. Yeah, this is a pickle lake. Last year I walked here doing field work. This is the fire base, right? I got fish from this dock. Okay, so this is the environment geochemical condition we discussed specifically associated with the nodules, right? Okay. Now we look at some independent data set, which is the pollen data. We also did pollen data for the whole interglacial deposit, right? You can see this is the pollen. You can see this is the pollen flora is dominated by spruce, pine, right? This is everywhere. This is very similar to what we see in this region, right? Today and in Hudson. This is very similar. So the pollen data actually looks very boring, right? You don't see much change here, right? However, so this is however, you look at carefully, and in the upper part here, you have a little bit of birch. The birch pollen has a higher frequency in here, right? And birch used to be low in it, because basically it's low, right? But suddenly in the upper part here, you have a sporadic rise of birch, right? Okay, in here, right? And also you have a little bit more alder tree, right? This is almost called alder tree here, and then a few more the oak grains in here, right? Okay, why the birch suddenly rise sporadically in this part? Well, this part right corresponds to this the interval where we have the these nodules were uncovered, right? Actually, we think this sporadic rise of birch actually is a result of the presence of frequent forest clearance by fires under hot and drier summer or warmer climate, right? Because birch cannot tolerate the shade, right? Say you have a closed boreal forest like today, go anywhere in Timmins, even here in Sudbury, go check that in the closed forest, right? And this is dark, it's humid, and in this kind of situation, birch does not grow well. Well, of course, here in Sudbury, in the city, you go everywhere, it's open, the birch is quite happy. It's everywhere is birch, right? So birch like openness, you need an open space, open clearance in the forest for there to grow. And the birch also like the mesic soil, I mean, the soil cannot be very wet, cannot be very dry, right? It has to be mesic, not very dry, not very wet, right? So this is for birch to grow. But basically, birch cannot tolerate the shade, right? So that's why suddenly you have a lot of birch. We think that's something to do with a lot of forest clearance at the time by forest fires, right? Remember that's Last Interglacial around 120,000 years ago, right? The clearance in the forest, we're gonna create that. Now we create a lot of clearance, forest clearance through logging, right? These forest logging, right? People logging, cut down the trees, they created clearance 120,000 years ago. So the only reasonable conclusion you can draw is that forest fires, right? Right now, see, probably you already noticed that during the last year, 2016, 2018, we had the climate was hot and dry in Northern Ontario. Then we have a lot of forest fires. And also in 2011, that's the worst year, because I've been in far north right here. That's the worst year. And you have so many forest fires going on there. That's because that time the summer was hot and dry, right? So this is the situation in the far north of Ontario. So we think this is independent data set from pollen also supports a warmer climate, at least as hot and dry summers for this interval, right? So these are conclusions, right? We think that these nodules, excuse me, we think nodules are likely a result of significant warming during this time, right? And and also at this time we have a lot of forest clearance created by forest fires at the time. So that's why during time we also have high birch pollen in the soil, right? That's what we detected for this interval, right? Okay, and so what? So we think that this warming probably linked to the last interglacial thermal maximum around 120,000 years ago, right? At that time, around 120,000 years ago, the summer temperature was 4 degrees to 5 degrees higher than today for the northern, middle, upper middle, and high latitude areas in northern hemisphere, right? I mean that, right? So you confirm, but at the time also we know that the global temperature was about 2 degrees warmer than today. So, okay, so the global, but we know for sure during last interglacial in the upper middle and high latitude area in northern hemisphere, so the summer temperature was 4 degrees and 5 degrees higher than today, right? So this is the same. We think that's linked to the thermal maximum at the time, right? Now there's some implications. So we know that this degree of warming, right? So 2 degrees warm annually, or 4 degrees, 5 degrees warmer in summertime. In summer, now didn't change the pollen flora, right? We show that, right? Basically, it didn't change that substantially in composition. However, we know that from all we talked, we studied, right? It did change the lake of the lake water geochemistry and the deposition. That means that water gonna have more hydrogen sulfide gonna be released from the lake floor, right? And the deposition, we're gonna have more sulfur bearing minerals like native sulfur or gray guy minerals gonna form on the lake floor, right? So this is seen when people studied the current lakes in Ontario, Northern Ontario, elsewhere, probably useful for them because we all think about the climate is warming, right? And we think that at the end of this century, we're trying to curb that temperature about 2 degrees warmer than today. It's not much higher than that. So 2 degrees is the target from 2015's Paris Accord, right, agreement. It is 2 degrees. That's what we can see here. If that's the case, using this record from geological record, we know that for sure. We have some record to show that the northern vegetarian forest probably not have a significant change, right? At least in the pollen flora, right? But however, the lake water geochemistry kind of change. You have a lot of hydrogen sulfide gas kind of released from the lake. You know that this gas is poisonous, right? This is poisonous, not good for fish and other aqueous animals to live on. This is a poisonous gas, right? Anyway, so that's it. So thank you for your attention.
Right, thank you, Dr. Gao. And the floor is open for any questions. Anybody has any questions, you can either type it in the chat or turn on your microphone and speak. Any questions? Just something occurred to me with this 4 to 5 degree higher and that 100. Are we in the ice ages now? Like, is that what usually climatologists, we're living in the ice age? Dr. Gao?
Sorry, I didn't get you.
Just asking a basic, like, from a geophysicist perspective, I don't understand. Are we living in an ice age right now with this?
Oh, right. Okay, yeah. No, we are in the most recent interglacial time. That's Holocene time, okay, right? Okay. We have a lot of, just follow up the question. We have a lot of discuss. So the last interglacial we're talking, this is the deposits formed during last interglacial around 120,000 years ago. So Holocene started from 10,000 years ago, right? 10,000 years ago. Last interglacial, the sister interglacial of our Holocene interglacial, right? So that's a good question. A lot of people say, how many good years gonna still be ahead of us? So we're gonna have next glacial ice age anyway, right? So how many good years ahead of us, right? So we don't know. So we are look at the sister interglacial stage. That is the last interglacial stage, right? Around 120,000 years ago. So that is exactly we are doing that right now. That people did a lot of dating that eventually they figured out that length, the duration of the last interglacial stage is from 130,000 to 116,000 years, right? So the duration is 16,000 years long. So Holocene, we already went through about 11,000 years, right? So that means we still have 5,000 years, good years ahead of us, right? Before the next major glaciation to occur, right? Yeah, thank you for your question. Yeah.
What really causes these glaciation rates? Like, do we know what the mechanism for this? What really?
Yeah. Now this is currently there is still we're not so sure, but most right now, most geologists believe that this has something to do with the Earth's orbital things, right? When Earth rotates along the sun, right? This kind of solar insolation gonna reach to the Earth, because this kind of Earth's orbit and the axis is gonna change, right? That gonna change the distribution of solar energy reaching onto the surface, right? So that say obliquity of the Earth's axis, right? This is goes back from 20 degrees, right? That's why we have 4 seasons, right? These things change, right? And because this kind of change, they have this kind of cyclic period, right? Around 100,000 years, 40,000 years period, right? So this kind of energy, solar energy reaching the Earth, gonna, particularly in the high latitude, they're gonna change that. And because of the change of solar energy, that caused this kind of repeating glacial. And
now it says mute. Can I now? Yes.
You gotta like Charles. You need to mute your microphone.
Okay. Now, how do I just ask him a question? It says mute now.
Now you can ask it. Are you Charles? You can ask.
That's right.
You're on mute.
Okay. Listen, I have trouble with all these gadgets on my TV, so I'm sorry about that. But George, you mentioned temperature all the time. Yeah. What happens with moisture fall or rainfall? Is there does that impact this story at all? Let's say we have a dry period, which we have several times in the last 12,000 years, where you have 100 years where precipitation goes down. Would this have an impact on your story?
Yeah, this is a very good question. Yeah, I mentioned temperature. Moisture, precipitation is hard to reconstruct, right? But basically, from we think during warming period, like right now, we say the warming, like current warming, right? The people projected from numerical simulations and modeling, they all project that kind of increased temperature along with increased precipitation, right? That's the case, right? So this, in generally speaking, I think during last interglacial, the total amount of precipitation could be higher, okay? However, there is a seasonal distribution that also matters, right? Is that the precipitation is the increase in rainfall or snowfall, right? Mm-hmm. And also you have, so that's one, right? Another thing is you have higher temperature, you're also gonna increase the evaporation rate, right? You have a lot of rainfall, but the higher temperature, the evaporation rate is gonna be higher, right? That also gonna affect the lake water, the water in lakes and the moisture on soils, right? So this is something we need to consider that, right? I think for this last interglacial, because we have very strong seasonality in that time because of high temperature, we think the climate that was more continental for the in northern hemisphere, say in northern in Britain. I did my PhD over there. I personally studied the site of last interglacial, and here in northern Canada. I think I just think this the last interglacial was more continental, right? Higher summer temperature, and but the winter temperature probably the same, right? And all the precipitation is mostly increased snowfall in the winter time. So this is something I think that right. Just to give you a very brief example, right? Say in the far north there, probably in summertime we have all, because I work in north, so I see that in summertime I stay there sometimes 1 month and 2 months sometimes, right? Sometimes you have a lot of precipitation, okay, but then afterwards you have higher. Summer is hot, right? You have a strong evaporation, right? You find still the lake level was low, the river level was low. Why is that important? Because I need a low lake level. So that's why I the place I can land my my helicopter to do geology, right? So that's the thing. So higher temperature, even have a little bit higher precipitation, that probably also gonna lower the lake level. And besides, I think this precipitation, increased precipitation during last interglacial is probably related to more rainfall precipitation at the time, right? Another thing I think is something I didn't discuss that is indeed if you have high temperature, high the evaporation rate on in the soil moisture, right? The lake tend to have a lower lake level. That's very important, right? Well, I didn't discuss that. I know that is too complicated. I think one paper cannot just you put out things and people can get confused, right? So lake level could be can be lower. That is very important because the lower lake level that's gonna increase the renewal time of the lake level exchange, right? The water gonna renew each time, right? At current setting, the renewal time in Northern Ontario is short, right? You analyze the lake water sulfate concentration in lake water is low. That's because the water constantly exchange with fresh water, so the renewal time is short, right? However, if we have a lower lake level and a higher temperature, then that renewal time is going to be short. The sulfate concentration is going to be increased in the lake. That's a good thing for this for the sulfur reducing bacteria to live on, and for this sulfate reduction process to go on. So that's something is important. But I didn't discuss in the paper and in this talk. This is something we need to discuss for future, but it's very complicated. But thanks for your question.
Okay, thank you.
There is a question by Dr. Richard Smith. He's asking what evidence is used to determine that the temperature was 4 to 5 degrees higher at 120,000 years ago.
Okay. Okay, I'll give me a second. That's a good question. Yeah, sure. I have something I didn't actually share this. Yep. This is we have a lot of these studies in the past. So also I contributed these studies, right? So this is the basic temperature with summer. We know that conclude for last interglacial, at least in summertime, right? There's a very nice review paper published in 2016 from a British scientist, right? In here you can look at that, right? This for Northern Hemisphere, we were almost sure that, right? So there's do I have something here? Okay. Sorry. I need to hide. Sorry, just give me a second. I need to hide this. Yeah, this is things I just hide. I didn't show that. I thought I don't have time. Right? This is last interglacial, right? This is global. It's just for here, and this is you can see this, during that time, southern Greenland become deglaciated with improved vegetation. These are all publications here. Now this is a this is a North American situation here. This is shows some the trees, because during last interglacial extended further to the north, right? This is something from geological U.S. geological survey data, right? You can see here. This is the tree boundary for birch, right? This today's boundary here. You can during last interglacial, the birch expanded further to the north. Into the northern part of the Baffin Island, right? You can see here the distance that you can see the scale here is about 500 kilometers, further north, right? Now the other thing you can look at is the hickory, right? This is the tree of hickory. Okay, now this one most typically in southeastern of the United States, right? But we have these things in Southern Ontario, in Toronto area, right? But if during last interglacial, this one grows here in the St. John's area, right? Most prominent feature is this liquid dambra, that's sweet gum tree, right? Now, this is typically growing in southeastern United States, right? This northern boundary never go beyond New York City, basically mostly south of New Jersey here, right? But however, during the last interglacial stage, you can see here, this tree grew in Toronto area. So right now, we have records on the Don Valley. So if you ever drive Don Valley Parkway, that's the site. The deposit is located on the right-hand side, right, in the Don Valley Park, right? So this is we have a Don Formation, right? Myself, I think did study in Southern England. So this is of last glacial study. So this is one of the very good sites for last interglacial. And from my side, I myself pick up a lot of seeds of this kind of maple, right? It's called Montpelier maple, right? This is a small tree or tall shrub, right? This is today is native to Mediterranean region, right? This is so this is not so adapt to growing in this kind of hot summer, very dry conditions. But at that time during last interglacial maximum, we have this tree grew in southern England, right? This is the tree leaves. So look at the leaves, very later feeding leaves, right? So we have a lot of that. There's a lot more of that, right? Although during that time, last interglacial, we have a higher sea level. I'm not sure I'd look at it. The sea level was about 6 meters. That glacial interglacial maximum at the time, around 120,000 years ago, the sea level was 60 meters higher than today, right? Anyway, so this is basically the data we compiled there. There's a lot more. You can go there. You can look at that, right?
It's compelling. You have the vegetation, sea levels, everything. That's perfect. Good.
Yeah, we have prepared, but maybe it's too much for people there. I don't think I have much time. I just prepared for questions like that. Yeah.
Perfect. Thank you.
Thanks.
Are there any other questions? If not, I thank you again, Dr. Gao, for volunteering to give this very interesting talk, and thank you everyone for joining the talk, and hopefully see you next week or the week after some Marine talks. Thank you.
Okay, thank you everyone for your attention. Okay. See you then.
Perfect. Thank you. Bye.
Bye.